So yesterday in the lesson we focused on graphing like coordinate points in the polar plane. And we did some simple equations, like really simple ones, where they were just the radius, so they turned out to be circles. Or if they were the angle measures, they just turned out to be lines. So those were pretty boring. Those are things that I would expect you to graph by hand. What we're going to be graphing today, while you will be graphing them by hand on your homework, when it comes to the test, it's going to be a lot of matching. So what you really need to know and focus on is, you know, if I was on a test, would I be able to identify which type of polar I'm looking at and kind of narrow down your choices that way? Well, that's what polars look like. Cute, right? They remind you of anything? Well, there's a polar bear polar, which I think is just so cute. Whoever thought to do that, yeah, you get a gold star for that one. Like these two in particular, do these remind you of anything from your childhood? Yeah, kaleidoscopes, yeah. Like the spirograph was what I was thinking. You young people not play with spirographs anymore? Okay. Jimmy Neutron? I don't know what that is, but I mean, I can assume what it is. It's a cartoon, I'm guessing. Okay. All right, so remember yesterday we were graphing ordered pairs and simple functions on the polar coordinate plane. They could be measured in degrees or radians. A couple of vocab terms from yesterday. What we used to call the origin is not called the origin anymore. This is called the pole. What you guys used to call the x-axis is not the x-axis anymore. This is called the polar axis. Thank you. I got an Abby and a Josh. It's the same for both radian and oh, sorry, Smith. So what we're going to do here is we're going to do one of these kind of sort of by hand, and then I'm never going to ask you to plot individual points by hand again, because this is going to be fun. So people who were having fun at Great America yesterday, I hope you know what we're about to do. We're about to graph some ordered pairs. Now, for the sake of convenience for us, we know that the ordered pairs for polars are r comma theta, where r is the radius, and then theta is the angle measure, which the angles always start on the polar axis and they rotate about the pole in a counterclockwise notation. So that should feel really familiar from like the unit circle. Thank you. But when we were graphing them yesterday, we had to start with theta. That's how you graph these, is you figure out where theta is located, and that's the line or the ray that you're looking at, depending on whether it's positive or negative for the radius. So what they did in this ordered pair table is they reversed it, so they put theta first. It's just easier for us to graph that way. So let's see what you guys remember from yesterday. If I asked you to graph theta equals 0 radians, that would be right here along the polar axis. So somewhere along here, we're traveling out to a radius length of 1. So that would be the first ring right here. And then this guy, so check. This next one, pi over 6 comma 2. It's actually reverse of that, but you're going to go to pi over 6, which is this guy, and then go out to the second ring. Pi over 4, 2.4. They don't label the pi over 4, but we know it's in between pi over 6 and pi over 3. So go out 2.4 rings, so like here. Pi over 3, go out to 2.7. Sure. Pi over 2, go out to the third ring. So then 2 pi over 3 is going to come back down now to 2.7. Oh boy. Okay, 3 pi over 4 is in the middle of this. So 3 pi over 4, go out to 2.4. Whoops, I missed. 5 pi over 6, go out to 2. At pi, go out to 1. And then it's going to start to get a little weird. So 7 pi over 6, which is this guy, they want you to plot a point at the pole. And then at 5 pi over 4, which would be right here, normally we'd be traveling along this side, but because the radius length is negative, you actually have to back up 0.4 units. So you're going to back up this away, and you're going to plot something about right there. 4 pi over 3, which is right here, but because the radius is negative, you got to back up. Oh boy. So we're going this way. Yeah, this is going to be tough for me to graph anyway, so it doesn't even matter if I got the point in the right spot at this point. All right, 3 pi over 2, that would be technically down this way, but because the radius is negative 1, you got to back up to 1. And then what's going to happen is you're going to end up with like a couple of ordered, it's going to make a little loop here. So I'm going to give up on trying to graph points at this point because it's going to get really bad, because what I'm about to do is actually graph. So there is a little loopsies here. And then oh man, I was starting so strong too. You know what? That's not bad. I'm going to call that a win. You guys just graphed a beautiful polar equation. By the way, I don't know if you caught the equation itself, but it was right here. It was 1 plus 2 sine theta. And that, my friends, is called a limousin. Say what? That, right there, limousin. Is that in your notes somewhere? Okay, cool. Circle it. Someone had to Google what that little mark was called. I already forgot. It's got a name. No, it's French. I don't really care about the French language. Sorry, French. Sorry, France. I just don't. I can hardly speak English at this point. Okay, so this is a limousin. You might want to put a little pronunciation down for your notes, a limousin. This technically is a limousin with an inner loop. What I want you to do in your notes packet, go to the very end of your notes packet real quick, and you guys are going to see a reference page. It's worksheet 10, and it's all the different polars that I could technically ask you, but the ones that we're going to focus on are the limousin and the roses. There's some really cool ones, like the spiral of Archimedes is really exciting. We're just not going to talk about it for a different class. But the limousin are in the second row of that worksheet, and there's different kinds of limousin. I don't expect you guys to know those from memory at all. But we're going to talk about roses in a minute. Those, I might suggest you putting a little energy and effort into, like memorizing how many petals there are, what's the length of the petals, because if you can do that for me on your test, you'll save a lot of time where you don't have to be on the graphing calculator and you'll go quicker through that section. Okay? So that's a limousin with an inner loop. It's already done for you, so that's very exciting. Okay, so here, let's look at the next example. This one's not done. Does that look like the same style function that we just saw? I shouldn't call it a function, but equation. So the one we just did was 1 plus 2 times the sine of theta. And what I'm about to ask you to graph is 2 cosine 2 theta. Do you suppose these are going to look anything at all similar? They're not. They're in totally different styles of equations. So rather than graphing this by hand, let's have our calculator help us out. So a few things I'm going to need you to do. I need you to change it to polar mode. So going to your calculator. Mine's probably all set up, but you guys need to do these steps, okay? Go to mode. Please change it to radian and polar. And then the other step I might suggest is for you to go to format, which is the second zoom key. And I might suggest you turn the polar coordinates on instead of the rectangular coordinates. The polar coordinates are going to be more exciting if you're trying to transfer to polar graph paper. So once you have all the modes set up, type in your function, which I lost my paper. What's the function? Is it 2 cosine 2 theta? Okay. The other thing you're going to want to do is you're going to want to adjust your window a little bit. Who knows what your window was? If you just, like on your test, for instance, the first section on your test is parametric, and your window will be all screwed up from parametric mode earlier. So when you flip over to polar mode later, you're going to have to adjust everything. So theta measuring from 0 to 2 pi makes a whole lot of sense. So if you guys can change the the theta min and max to 0 and 2 pi, that'd be good. I think it automatically adjusts your step for you. But for x's and y's, you don't know enough about this creation to know how long it's going to go in either direction. So let me just tell you, you should go like smaller than 10. I'm just going to go -5 in each direction. -5 to 5 for x, and -5 to 5 for y. So when you hit graph, you should see that. Now, this is a little skewed, because remember, we're taking a polar thing and we're graphing it on what is essentially a rectangular grid, so it's skewing it a little bit. So if you want it to square off, at this point, you guys could hit zoom square, which will make it look the appropriate, like, it won't skew it anymore. It's going to make it look rounded. That's what it really looks like. So anyone want to take a stab at what this is called? I have already said it today. It's a rose, of course. I think it looks not like a rose at all, but they call it a rose. So it's a rose. And what do you think these little pieces are called? Petals. Isn't that precious? Okay, so what's kind of neat is from the rose's equation, you should be able to tell me some things. For instance, just without graphing it on the calculator, what I expect you to be able to do by the end of your homework assignment is to look at this and go, oh, well, I can tell you how many petals there are and how long the petals are. So this, anything in the form of a number times the sine or cosine, and then inside the sine or cosine function, you're going to have another number and then a theta. If it's in that form, you have a rose. So here's what these numbers tell us. Whatever number is in front of your sine or cosine function, that is the length of the petal. So in our question, apparently the length of the petals was 2 units. And if I go back to my calculator, and I pull up the cursor, if I don't see my grids enough, traits, yep, indeed, it goes out to R2. Now the number that's inside the function is a little confusing. If this number is odd, then whatever that number is, it equals the number of petals. So if there's a 1 inside of there, or a 3 or a 5, that's how many petals you have. However, if the number is even, then you're going to take 2 times this number, and that is the number of petals. So like on this question that we just did, there was a 2 inside of the cosine function, which meant that was even, obviously. So if you multiply that by 2, we knew there was going to be 4 petals, and that's what you saw on your calculator. Now where those petals are located is going to be based in symmetry. We're going to come back to the symmetry idea in a couple slides from now. So for now, I'm just going to kind of fudge this onto my paper, and this is where everyone started laughing at me last hour, because, yeah, this isn't going to go well. Okay, so do the best you can. Mrs. Hoffbauer was very sweet and gave you all polar coordinates to transfer like your homework right onto there. It's going to be beautiful. She even made them really small, which I know seems like a bad idea normally in math, but on polars, a small coordinate plane is good news. Yeah, so I'm supposed to get the petals to look the same. Okie dokie. No. No. It's like I start out with a real good one, and then they get like, well, yeah, that face. That's what I got a lot of first hour. They're like, oh boy. Yeah, the key doesn't look any better. So I'd like to blame it on the tablet. It's not the tablet, it's me. It's just me. That's not good. Okay, so that's a little note about the petals and the length of the petals and how many petals there are. Let's see some other examples here. So this one, I believe, is on your notes. Why did I put my notes away? Huh. So this kind of sort of looks like the formula for a rose. We said it was a number times either sine or cosine and then times something theta. So I would argue that there is secretly a number inside with the theta. There's secretly a 1 there. So we have a rose, for sure. But it's a very special rose. Without using the calculator, I think we can tell a lot of things about this rose. For instance, how long are the petals? Yes, the petals are 2. And then how many petals are there? So inside of the function, there's a 1, which is odd. And when that number is odd, that's how many petals you have. So you're only going to have 1 petal. So what would that be? You just have 1 petal. That's a circle. Okay, so you might be wondering, like, where the heck is this circle located? You don't know about symmetry yet, so you just have to trust your calculator or your teacher at this point. So, yeah, it's okay. Oh, gosh. It's like it gets worse, right? That's a circle. If anyone is going to argue with me, it's a circle. It goes from the pole up to 2. That's how I know it has a radius of 2, and everything else there is just, give me a little grace, okay? It's beautiful, Mrs. Abruzzo. Good job. Okay, is this one going to be a rose? No, it is not in that formula. There's like a random 2 plus at the beginning. So then a good assumption on your part might be, oh, maybe it's like that first one we graphed, that Lemus thing. And it is. It is a type of Lemus. But can you guys look at worksheet 10, where it shows all the different Lemus? There's a bunch of them. So it's one of them. Definitely one of them. And you guys are too new to this to know what kind of Lemus it is. So let's just graph it on our calculator. So 2 plus 2 sine theta. Let's get that entered. Some of you already figured it out, you smarty pantses. 2 plus 2 sine theta, was it? I heard some guys predicting it was a cardioid. Now, you can be honest with me. You saw that drawn, would you be like, clearly that's in the shape of a heart? Because that's what they claim. Okay, you're a very mature class, because that's not usually what kids tell me. They go, it looks like a butt. And I go, I can't disagree. But mathematicians aren't going to go around calling it a tushy. So they're going to go with it's heart-shaped, and therefore they named it cardioid. Oh. Yeah, that's sure. Anywho, you guys don't need to have that memorized. You're going to use your calculator when the Lemus come up, because you're not going to be familiar with them. I'm supposed to be able to draw that. Here we go. Does that go up to R4, right? Okay, here it goes. 1, 2, 3, 4. Oh. You can't unsee it though, right? Like, yeah. Alright, here we go. Moving on. Anyone have a thought about that one? Definitely not going to be a rose, because it doesn't fit the format. It's one of the weird Lemus. Maybe you've already figured out which one. And if you haven't, it's okay, because you're about to graph it on the calculator anyways. One minus, was it 3 cosine? Which one do you think it is? Well, it looks like that. So this one always confuses kids with the formulas because I think they are a little fast and loose with their negatives. But this is called a Lemus with an inner loop. But, I know, you guys are looking at that going, but that doesn't fit the formula that's on there. Yeah, I know. It's very confusing, okay? It has to do with the difference between the A and the B value. It's just, don't look into it, guys. It gets very confusing. Okay. So, this is a Lemus. Hey, does Lemus sound like anything to you? In the legume family, perhaps? Beans. Lima beans. These are supposed to look like lima beans. That's, I think, the derivation of Lemus. These mathematicians who came up with these names, I am not... Apparently it was the French, and you know how we feel about the French and mathematicians. They are the weird ones with the natural log as ln. Man, all right. I don't even know if that's true, Internet. Sorry. Okay, so that's a Lemus with an inner loop. I don't need you guys to hem and haw over, how did she know that? I didn't know it until I graphed it, okay? So could you please transfer this to your paper and make sure that this inner loop goes out to an R of 2 on the negative side though. And then the big loop goes out to 4. And then do the best you can, please, because, yeah. What? I know, the French government's going to come after me. I'm so sorry. I apologize. I love everything about you. I'm making it worse. Stop talking about the French. I don't even know if anything I just said was true. This video is going to be garbage, too. Oh, my gosh. The other video I didn't even name. It was so bad. So bad. Okay. I'm so sorry. You're right. It does look like a heart. You're absolutely correct. Okay. Guys, there's a little note here about symmetry. So we can't use the same symmetry laws that we used back in the rectangular coordinate plane because we have totally different axes. So when you have something that appears to have what you used to call y-axis symmetry, we don't have a y-axis anymore, right? This is not called the y-axis. This is called the line theta equals pi over 2. So if you see something that has that sort of symmetry, you're going to have to write that it has symmetry with respect to, yeah, I know, theta equals pi over 2. The other thing you might want to write down here is that if you notice your graph has this type of symmetry, it's going to be based as a sine function. Okay? And that applies to Lemus and roses and everything, okay? So if there's a couple homework questions where they give you the graph and they want you to figure out the equation. Well, obviously one way to do that is just start typing stuff in your calculator until you get it close. But if you're trying to go like, oh, is it sine or is it cosine? You're gonna have to look at the symmetry. So if you have something that kind of appears to be x-axis symmetry, but we don't have an x-axis, we don't call it that anymore. We call this axis the polar axis, okay? So if you notice that's what's going on, then you have symmetry with respect to the polar axis, and that's going to be a function, an equation that's based in cosine. No, yes, cosine. Okay. And then you can also have what appears to be origin symmetry, but remember we don't call the origin origin, we call it the pole, so that's what it would look like as well. I don't think they don't specify like which ones have polar or pole symmetry. It's not the kinds that you are going to have to worry about. I think it's the weird ones that we're not graphing. Okay. And I'll be honest, guys, if I was a high schooler and I was doing this homework, I probably wouldn't hem and haw over the symmetry when I get to those questions. I would probably go, maybe it's cosine, and then I'd type it in my calculator, and I'd look and I'd go, oh, apparently not, and then I'd switch it to sine, and then, oh, there's the answer. So you guys are going to have to know certain things about these functions just to make your test go smoother and quicker, okay? That's all I need from you. Can we go back and do, real quick, these three, and let's talk about symmetry? For instance, this one here. Notice how this, it's technically a rose, but it's turned out as a circle, has theta equals pi over 2 symmetry. So if I asked you to write this out for homework, you would have to say symmetry with respect to theta equals pi over 2. Now notice how the basis of that equation was the sine function. Okay, so if I gave you the picture, which I wouldn't, but a computer would, and you had to somehow figure out what the equation was, you at least knew it was based with sine. So same thing here, same sort of symmetry of the theta equals pi over 2. What about this guy? That's symmetry with the polar axis, which is what we would have called the x-axis. And that means it's a based in cosine function or equation, which it is, based as a cosine. All right. Let's move on. Oh, this is all the reference page stuff. Aren't these cute? So circles, which are really just lame roses. And then limesons, which are funky little lima beans. So the inner loop we've seen a couple times. We saw the cardioid. Oh, I spelled cardioid wrong earlier, didn't I? I put a T in it. I always spell it wrong. It's a D. Yes. A dimpled lemison. It's... No, there is a difference. Visually, what's the difference? I don't even know. I can't tell. I would only be able to tell because I would look at the function, and you can compare the values of A and B, and that's how you can algebraically tell which one's a cardioid and which one's a dimpled lemison. I'm not going to do that to you, though. I'm not going to give you something sneaky like that. Yeah, I'm with you. They look the same to me. I don't know. Some dude was like, I want to give this one a new name. Ask the people. No, please don't comment on my video. Okay. Roses. We've seen them. We love them. They can have all sorts of different petals. We've discovered how we determine the number of petals. That was fun. Can you guys notice the sine roses versus the cosine roses? It has to do with the symmetry, okay? The symmetry. All right. Skip all this stuff. Go to the back of your worksheet. Can we look at this one? This is the kind of stuff you're going to see for your homework. You guys got to tell me to be quiet in a few minutes, remember. Okay, talk to me about, there's only two choices here, guys. Is this a rose or is this a lemison? It's a rose. So talk to me about this rose. What do you know about the lengths of the petals? Yes, so the petals are a length of 4. And because the inside number is odd, that means we're going to have 3 petals. So where are these petals located? From memory, that's kind of tricky. So you guys would just graph it on your calculator. But since I'm kind of short on time, if you wouldn't mind, I'm going to attempt to draw this. Hang with me. Okay, the first petal goes down to yonder. Oops. And then they're supposed to be symmetrically placed about the pole. So this next one will be over here. Like the 4. Gosh, be golly. Thank goodness I can redo that. 1, 2, 3, 4, like I said. So that guy has to go out, huh? Did I go too far out? 1, 2, 3, 4? Okay. And then, so it's at pi over 6, and this guy would be at 5 pi over 6. So 1, 2, 3, 4. Woo! That's so ugly. Okay, so kind of looks like a propeller? No, it's a rose. Silly children. It's clearly a rose. I do not expect you to know where the petals are placed from memory. That would be a definite, like, here's what would happen on your test, guys. It would be a multiple choice question. And if you knew from your choices that you had to find a rose with 3 petals, there would just be one of them. Okay? That's all I would ask of you guys for a test. There are multiple choice questions, yes. What is this guy? It's a rose. Tell me about this rose. Length of 3. And there are 4 petals. Because the number inside is even, which means we have to double it. Alright, they're along the axes. Let's see if I can do it right this time. Maybe not. 1, 2, 3. 1, 2, 3. 1, 2, 3, and 1, 2, 3. I heard you all holding your breath for that last one. You were like, oh, she's gonna do it! And I didn't. It's okay. It was close. It was much better than first hour. Sorry, first hour. Alright, real quick. Multiple choice question for you. Well, what are we looking at, guys? 3 cosine 2 theta. It's a rose! Are you getting the importance of a rose to me? Apparently, I'm really excited about the rose equation. Those are the easiest ones for me to ask you about on a test. Lemesons are kind of crazy looking. So don't be surprised when you see a rose on your test. I could ask you for a lemeson, and in that case, just trust your calculator that it's graphing it properly. Alright. You have homework on that. There's a follow-up book assignment. Mrs. Hoffbauer gave you some pole coordinates on the back of the assignment. Sorry, you got to keep flipping. But those of you who aren't doing your retake right now, I would just start working on your homework because you're going to need to graph probably all of them. So just now that your calculator's in the right mode, just start typing away.